Welcome to Chem Help ASAP. So this video is a reaction video, and that's a departure from my normal content. Normally I do educational videos, but my son was watching a video on YouTube where this person was just doing all kinds of crazy chemistry. And I was like, what are you watching? He said, this is NileRed. Now I'm aware of NileRed. And so I sat and watched the video with my son and I said, I would have done that differently, or that's really cool. And so I thought, well, let's try to do a reaction video off this. I will have some criticism and I will have some praise, but I'm not trying to stir up any trouble here. There is one thing that I've done to this video. For NileRed's video, I've played it back at 1.5 times speed because it is a little longer and I wanted to shorten it where I could. I've maybe edited a couple clips. I'll call those out as we go through. So, welcome to my first reaction video. I hope you enjoy it, and let's see what NileRed has going on.
This video has been sponsored by Ground News. Over the years, I've done many projects where I turn completely inedible things into food, like that time I turned plastic gloves into grape soda and hot sauce, as well as that other time when I turned cotton balls into cotton candy. What I've been really wanting to do for a while, though, is to try turning children's glue into drinkable alcohol, and at least in theory, this should be possible. This is because the main ingredient in most children's glue is a plastic called polyvinyl acetate, or PVA for short.
Okay, I have to pause it here. So, polyvinyl acetate is PVAc, not PVA. PVA stands for polyvinyl alcohol. It's a different substance, similar, but different. I don't want to be too nitpicky, but later in the video, we'll see some literature information, and it'll all say PVAc because this is polyvinyl acetate.
And in its chemical structure, it contains all of these little groups here in blue, which are known as acetate groups. On their own, they aren't too special, but what I think is really interesting is that it should be possible to pull them off the PVA and to turn them into something known as acetic acid, which is essentially pure vinegar. Then after that, with just a bit more chemistry, I should be able to convert this acetic acid into some pure ethanol, which hopefully would be safe to drink.
Okay, if it's pure ethanol, it's safe to drink. As much as you want to drink pure ethanol, in moderation, of course, but if it's pure, it's safe.
With that being said, though, overall, I just thought that this whole idea sounded pretty fun to do, and I was also really curious to know what children's glue alcohol would taste like.
Okay, does school glue convert into alcohol that tastes like a school? I don't know. We're going to see.
So, despite the fact that I wasn't exactly sure how to do it, and that I very possibly might end up just completely failing, I decided to just go for it. So I just went ahead and got started, and the first thing that I was going to need was, of course, some children's glue, and I ended up going with Elmer's.
His lab has a drawer for glue. It must have everything in it.
Which seemed to be the most common one. I also decided to go with a full gallon, which is about 3.78 liters, and this may seem like a lot, but I had
that does seem like a lot. Essentially 4 liters, that is a lot. 1 gallon.
Absolutely no idea how much PVA was actually in here, or how efficient the process would be. But with that being said, now that I had the glue...
Now this is beautiful. Let's watch that again. Watch this edit.
How much PVA was actually in here, or how efficient the process would be. But with that being said, now that I had the glue, it was time to try turning it all into alcohol, where the first step was to get a large dish and to start dumping it in.
Okay, so this is, let's just manage some expectations here and look at some numbers based on the amount of glue that's being involved here. Okay, so here's our glue. We have 1 gallon of glue, and this is almost 4 liters, just short of 4 liters of glue. Now you can look up online, the density is 1.07 grams per milliliter, and that means the mass of this 1 gallon, nearly 4 liters, is 4,040 grams. Now, if this is pure PVAc, then that means that this material is 73% acetic acid by mass. 73% of 4,040 is 2,950 grams approximately. And if you could perfectly convert all that acetic acid into ethanol, we're looking at over 2 kilograms of ethanol. So these numbers just give us a sense of what's possible with a key assumption if it's pure PVAc at all. Now, I'll tell you it's not, and we're going to find that out. But just to give us a sense of what's possible with this reaction.
This was because before doing any chemistry, I was going to have to get rid of all the water that was in the glue.
Okay, this is kind of key. So he's dumping out this glue, and note my cursor's awfully small there, but note the level of depth of wood glue in this casserole dish. It's just about full. This is a lot of stuff. This is important because we're going to look at this level and see how it shrinks, and we'll make some judgments about what's going on here.
Which was at least around 50% of its volume. I also figured that this was going to be...
Now, he said water, he thinks it's about at least 50% of its volume. So that's a good idea. So all those estimates that I had, we'll get about 200 or 2 kilograms of alcohol from this. If it's 50% water, then half that mass is gone. We're only going to get 1 kilogram of ethanol. So how much water in there is going to determine how much PVC there is in there for him to degrade it and actually get acetic acid and ethanol.
Really simple, and that I basically just had to leave it out to dry, and I assumed that this was going to go relatively quickly.
Nice.
However, that was not at all the case, and it turned out that drying glue like this was excruciatingly slow, mostly because the surface of it just quickly formed a really thick layer, which prevented the water below it from evaporating. To fix...
So I'm going to talk over him a little bit here. So this is a pain. When you're trying to remove water from something thick like this glue, I mean, it's hard to get water. Water doesn't dry out very well because actually for its size, it has a pretty high boiling point. So, it's no surprise that this is difficult because this is difficult.
Finally accepted that this was an absolutely horrible method that would probably take at least a few more months, and it was pretty clear that I was going to have to try something else. So I decided to basically just do anything that I felt would speed it up, where the first thing that I thought of was to chop it up like a large cheesy lasagna, which I thought would really help the moisture escape.
So anything to increase the surface area will help the evaporation process, and that's exactly what he's doing.
I then tossed the whole thing into a food dehydrator to heat it up, and after a full week, it was looking significantly better.
Okay. He's right. It's not significantly better. It's apparently not to what he wants this to be. But do notice, look how low that level is. This has lost a lot of water, way more than 50% by eye, maybe closer to 70 or 80%.
However, after manually tearing off some of the glue and peeling away the rest with my multi-tool...
Okay, power tools and glass dishes, there's some risk there.
It was obvious that it still wasn't fully dry, and I'll be honest, after waiting almost a month already, I was really tempted to just consider this dry enough. As one last
okay, we'll see how dry it has to be.
effort though, I decided to try putting all of it into my new vacuum oven that I just happened to get earlier that week. With it all loaded in,
The vacuum oven is the right tool for this job. This is a perfect use for a vacuum oven. He's going to pull that water right out, heat it up, and evaporate it out.
then pulled a vacuum on it, which would make it way easier for the moisture to escape the glue, and I ramped the temperature up to 80°C. I also kept it there, and I didn't raise it any higher, because at least from what I read online, anything hotter could potentially cause the PVA to start degrading. But either way, as the glue...
That PVA degradation is coming, or PVAc degradation is coming, but not yet.
glue sat there, it did slowly get drier and drier, and eventually, after several more days, it seemed like all of the water had finally been removed.
So there is a way to make sure or to determine whether you've removed all the water. And you could take this dish out, you could weigh it with its contents, put it back in for a few hours, weigh it again, and you would dry it to constant mass. Now that doesn't mean it's dry, but it means you've gotten out everything you're going to get out. So you don't have to guess about this. You can actually be more certain. And maybe he did that, I don't know, but that's what I would do to be more confident that the water's gone.
So I took it out, and now, after what was way too much effort and work, what I was left with were some super dry blocks of what was probably nearly pure PVA. At this point, it was also probably as dry as it was ever going to get, so I just went and got my multi-tool, and I fully chopped it into pieces.
Okay, that looks like a disaster.
This then left me with a bunch of rock-hard blocks of glue, which I was pretty happy with, and after weeks of kind of wasting my time...
Okay, I am going to skip ahead a little bit. He's got a problem now. He's got his glue and it's dry, and that's a good thing. But he's got to get it into smaller pieces because he's got to fit it into this glassware that has kind of small neck on it. So he needs this chopped up. So let's skip ahead. He's going to get actually a wood chipper, and he's going to throw the stuff into a wood chipper, and he's going to get something that he can work with. Okay, so he's put this into a wood chipper. He's got smaller pieces. These are looking better, so let's continue.
And over. This then caused the pieces to gradually get smaller and smaller until eventually I was reaching the limit of what the chipper was able to do. So I decided to stop here, and what I had now was a beaker full of small chunks of PVA, and what was nice was that they were all pretty much exactly the size that I wanted them to be. It was also very nice that this had only taken about 20 minutes instead of hours and hours of tediously chopping everything myself, and I'm very happy that I invested in the wood chipper.
That is a win. Look, he looks so happy because you can imagine how hard it would be to manually break all this stuff up. So this is a huge win.
Moving on though with all of the glue.
Okay, so this is now our first peek into what he has. So here's the ground up PVAc, and it's in there. And let's get a cursor here. So you can see this is a beaker. It has graduations. We can read some volumes off of this. These are very approximate volumes, but we'll do what we can. So he has less than 2 liters of these glue chips, and it's even less than 2.5. And I would even say it looks to me like this material is kind of sloped downward a little bit. So it's even less than 1.5. I'm going to guess it's 1 liter. 1 liter of chips, and there's a lot of air volume in there. So it may not be crazy to say there's really about 500 milliliters of this material in here. And remember, we started with, and that's a half a liter. We started with 4 liters, or close to 4 liters. So we've lost a ton of volume. Presumably that's all water. So how much we can get from this 1 gallon of wood glue is going to be way less than the optimal or the optimistic estimates I have had in the middle of the video.
Now ready, I could finally start doing the chemistry to turn this into some hopefully tasty alcohol, where the first step was to turn it into pure acetic acid.
Okay.
From a bit of research, it also seemed like there was probably a few different ways to do this, but from what I could tell, the best and easiest way was to basically just heat it up.
You know, just heating stuff is generally not the best way to accomplish things in a lab. But, you know, we'll see what happens. Yeah.
So that was what I decided to do.
And, you know, I'll just hesitate right here. PVAc, that is PVAc. That is, it's not the same as PVA. These are different things. So we're talking about polyvinyl acetate, not PVA, polyvinyl alcohol.
And to get started, I just quickly transferred all of this glue into the biggest round bottom flask that I had.
That's a big round bottom flask.
I then dropped it into a big heating mantle that I bought just for this, and I clamped it in place, and I continued putting together the rest of the setup by first adding a 3-way adapter with a thermometer in it, followed by a condenser column. With all of this in place, I was then able to quickly finish putting it all together, and only a few minutes later, this was what I had, where the flask here was where I was hoping to collect the acetic acid, and the tube here was connected to my vacuum pump. This was...
Okay, so he's going to heat this up, this flask, in this heating mantle, and he's just going to drive out this acetic acid as the polymer degrades. And it is going to come through this arm and drip down here, and he's under reduced pressure, so that's a vacuum line. This is heating something to degradation is a pyrolysis, and he's doing this under a vacuum. So I would call this a vacuum pyrolysis.
It's very important because this all had to be done under vacuum and without any oxygen present, otherwise the glue would probably just burn or become a crusty, charred mess. With all that being said though, I was just about ready to get started, and the only other thing that I still had to do was wedge a thermocouple between the flask and the heating mantle. This would allow me to monitor the temperature, and it wouldn't be super accurate, but it would still give me a decent reading of how hot the flask was.
Yeah, very often you want to know the temperature inside a reaction, but the process of sticking a thermoprobe in there is going to cause problems in the chemistry. So often the best you can do is stick something directly against the glass outside of the reaction. And it's not perfect, but it gives you an idea whether things are getting hotter or colder, and oftentimes that's all you need.
Now with all of this in place, it was finally time to start cooking some glue, and to get things going, I started by flipping on my vacuum pump. I then turned on the heating mantle as well, and I raised the temperature dial only slightly because the goal now was to heat things relatively slowly. This meant that at first, not much was going to happen, and well, over the next 10 minutes, I really didn't notice much of a difference. When it eventually got to around 70°C though, I started seeing some fogging down here, and not too long after, I saw the first drop of liquid fall into the other flask.
You know, when you heat things up, it takes a while to build up heat. there's a lot of stuff that has to get warm. So it does take time, and nobody's patient. So everybody just wants stuff to happen right now. But you got to be patient and let the reaction do what the reaction wants to do.
However, when I looked over at the thermometer, which was showing me the boiling point of the stuff that was coming over, I saw that it was only around 20 C, meaning that this was probably just residual water that was getting cooked out of the glue.
This isn't a surprise. What would be a surprise if he had successfully driven all the water out of that glue. Of course there's a little residual, and he's going to see that start to get driven out even further as he does this.
It then continued just like this for the next 20 minutes or so, where I got more or less continual drips, and the temperature of the glue flask slowly increased. This in turn made the drip rate increase as well, and when the glue eventually got to around 160 C, the stuff coming over started turning yellow, which I thought was a very good sign. This was...
I mean, it's a sign something different is happening. And he doesn't want water, he wants acetic acid. So it changed. This is, I agree, this is a good sign. I wouldn't be happy about the color coming over, but it's something different. Something's happening.
It was because it likely meant that the glue was starting to degrade, and even though what I was collecting was probably still mostly water, things were at least moving in the right direction. But either way, all I could do now was just keep waiting and hoping that the glue would really start breaking down, and well, eventually, several minutes later, that was exactly what seemed to be happening. This was because at this point, it had...
So he's heating this stuff up, and it is degrading. And when things degrade, they tend to discolor. And so this flask is starting its discoloration phase because the degradation is beginning. So again, this is a good sign. You hate to see things look worse, but sometimes you got to break an egg to make an omelet. So that's what he's doing.
Not only become significantly more yellow, it was also starting to let off some smoke, which was then traveling through the rest of the setup and filling up the other flask. I actually didn't know exactly what this was, but according to a paper that I found, most of it was supposed to...
Okay, let me move myself over here. Okay, so this is released gas products from treated PVAc. Note this is polyvinyl acetate, not polyvinyl alcohol. And there are a number of things that can get released here, including what he wants is acetic acid. And that's the bulk of what he ought to get off of here. All this other junk is, when you drive the acetic acid off this polymer, you leave that polymer backbone. And that polymer backbone, you're heating it up, it can also do chemistry and degrade into different things. And those are some of the products that we're seeing in this list.
To be the acetic acid that I wanted, which was forming as the acetate groups on the polyvinyl acetate, slowly got torn off. The rest of this vapor, though, was supposed to be a bunch of other crap like acetone,
other chemicals, other crap, kind of synonymous, I guess.
And carcinogenic benzene.
Benzene, that's not a very stable molecule. Not surprising this thing would degrade into more stable compounds like benzene.
Which was forming as the PVA plastic in general was breaking down. This in turn meant that in the end, I was probably going to end up with a horrible concoction of nasty chemicals, which wasn't exactly ideal, except that was something that I could worry about later on. But either way, getting back to the reaction, I quickly put together a little ice bath to try and help and condense the vapor, and when I looked back at the main flask, I noticed that the glue was significantly darker. From there, then only continued to get darker and darker, and eventually, by the time the flask was at 200 C, it had developed a nice red color, and there was some nasty black...
That was a nice time lapse. Things do tend, if you just heat them up, they're going to get darker and darker, and that's going to be a progression.
Black liquid that had collected on the side of the flask. At the same time, the liquid that was coming over had also gotten a lot darker, and just by the color, I could tell that it was filled with a bunch of horrible and potentially carcinogenic chemicals. However, despite this, I was still very happy with how it was all going, because at least in theory, this was all still mostly acetic acid, and at this point, I had collected a pretty decent amount.
If that's mostly acetic acid, I agree. This is looking pretty good. Better than what you would typically see when you just heat something and hope you get something out of it.
From what I could tell, the rest of the distillation was also relatively straightforward, and I basically just had to keep heating it until the acetic acid stopped coming over. I, of course, had absolutely no idea when this would actually happen, but after about an hour, the temperature on the thermometer started rising much faster, which told me that I was starting to collect something else. I think we're getting to a completely new fraction here. Most of this was still probably acetic acid, though, so I decided to keep collecting it until it got to around
This happens. You know, when you're running something and you're gathering material, you don't want to lose any material. You don't want to leave anything behind, especially because you're feeling tentative. You know, let's keep pushing. Let's get more and more and more. Every organic chemist experiences this. You want to maximize that yield. Sometimes that pushes you to make mistakes, but everybody understands this if they've worked in lab.
120C, which was over triple the boiling point of pure acetic acid under the current vacuum pressure. At this point, there was probably almost no acetic acid coming over, and the rate had also slowed down like crazy, but I still wanted to keep going, just to be absolutely sure that I collected everything.
That's right, let's get everything. I want everything.
This didn't end up going on for very long though, because only a few minutes later, the temperature of the flask quickly spiked from the 230C that it was at, all the way up to 380C, which I really didn't like.
That's a big temperature jump. So what's presumably happened is all the heat energy that's going into this flask is causing the decomposition of this polymer, releasing acetic acid, and he's seeing that collect in his receiver flask. But at some point when that process ends, you're still putting heat into the flask, and now that heat energy is no longer going into a decomposition, but it's simply just raising the temperature. And so he's right. This is done.
And like that, it just went up 150 degrees in like 30 seconds. So I think it's done. I think it's... This highlights a point. When you run a reaction, you really need to monitor that reaction because things can change quickly. And he was monitoring it. He was on top of it, and so he noted, hey, something's changing, and it's changing in a way I don't like. Before he liked changes, but now he doesn't like this change, and I think he's right. This is a bad change, at least if you're trying to collect acetic acid. There's like nothing left in the flask. I'm not heating it anymore. I'm done. So I just went ahead and ended it here, and I turned off the heating. I then went over to the other flask, and I got rid of the dish of cold water, and what I immediately noticed was that it had actually separated into two distinct layers.
Wow, now this is a lot of stuff. So this is kind of hard to read, but this is about 1,000 milliliter flask. And he's almost halfway. Halfway in a flask is typically more than... it's less than half its volume. So 1,000 liter flask, you think, oh, halfway, this is 500 milliliters. They don't tend to work. This is probably closer to 4 or 450 milliliters. So regardless, he's got a lot of stuff in here. Remember we talked about how that polymer was sitting in that beaker, and I said, maybe that's 500 milliliters of stuff. It looks like he's gotten a ton of stuff off of that polymer. So, well done. This is way better than I would have expected.
This told me that there was for sure a whole bunch of nasty crap in there, and I was pretty certain that the black layer on top was mostly the carcinogenic benzene.
This is biphasic. I don't know what's in there. I just lost my lights in my office. I don't know what's in there, but this is... It's likely the big part, the bottom part, is acetic acid, and that whatever the top part is, it is not miscible, not soluble in acetic acid. So, he's got to do something about that.
Moving on though, I then popped off the flask, and the moment that I took it out of the fume hood, I was hit by the smell of it, which can only be described as a mixture of burnt plastic and gasoline, and it pretty much gave me an instant headache.
Yeah, this is probably pretty gross stuff. When you heat stuff up to the point that it just breaks apart, you're going to get all kinds of junk. It's going to stink, and, and sure enough, it stinks.
In my mind, this really reinforced the obvious fact that there was a whole bunch of nasty junk in there, because pure acetic acid should have smelled much more like really strong vinegar, and I was definitely going to have to clean it up. So that was exactly what I started doing, where the first step was to pour it all into the biggest separatory funnel that I owned, and to let it sit there for a bit for it to separate.
So this is a separatory funnel if you're not familiar with it. This is a classic piece of glassware for separating immiscible liquid layers. This is a liquid-liquid extraction, and presumably that he'll be able to use this to separate these letters, or these layers.
Right back into two layers. This then happened extremely slowly, and even several minutes later, it was really hard to see any difference, but I felt that it was good enough, and I started draining.
Good enough. That looks pretty rough to me, but that's okay. He's going to run with it. So he's draining off that bottom layer. That was the major layer, and presumably that's where his acetic acid is. So he's gonna drain this off the bottom.
Everything into a large beaker. At the same time, I also looked very closely at the separatory funnel to track where that upper layer of nasty black crap.
So he's watching this. Presumably there is the dark top layer on the top. You can see this is a little lighter as it goes through the narrow part of the glassware. And this will, he'll be able to see this dark layer move down, and then he'll know when to turn off his stopcock.
Crap-wise.
I'll try to stop it.
When it eventually...
Okay, there was a layer. Let's just go back once and see that again. Watch really closely right down here. This is where the action is. And he lets it drain through.
Separatory funnel to track where that upper layer of nasty black crap was.
Oh, I tried to catch it.
And
come on, baby.
when it eventually...
There it was. Okay, so he caught it. He separated. It's not a perfect separation. I might have tried this a little more, but listen, he's doing great.
got to the bottom of the funnel, I closed the valve. I then quickly got rid of all of this mystery oily junk, and now when I look...
Yeah, that's garbage. He doesn't want that. It's not miscible in his main layer, assuming the main layer is acetic acid.
Over at the stuff in the beaker, I felt that it was already looking a bit cleaner, which was good. It was still super dirty though, and I would of course have to do a bit more work, except before doing that, I wanted to do a quick test.
So how does he know it's super dirty? Because acetic acid is a clear colorless liquid. That is obviously not a clear colorless liquid. There's something in there, and he knows that. But I think he wants to confirm that this is acetic acid.
More specifically, I wanted to do a pH test because up until now, I had...
Ooh, I like this cut too. This looks like James Bond opening up a cigarette case and offering a cigarette to someone. Let's see this again.
I had to do a quick test.
Go. Okay.
More specifically, I wanted to do a pH test because up
James
until now,
Bond.
I hadn't really done anything
good,
to confirm
good.
that there was actually any acetic acid in
So
here.
that's his pH
and I'd
paper.
basically been going on pure hope. So with that being said, I just went ahead and tested it, and I was kind of worried that it would show...
Okay, I'm interrupting him a lot here, but notice the volumes. So this is 500 milliliters. He has less than 500 milliliters. And based on the space of that graduation, which is another 250, let's say he's 125 or 150 below that 500. So he's around 350 milliliters of distillate. And this is actually not distillate. He's done an extraction on this, but what he thinks is the acetic acid portion of the distillate, I'm going to guess is about 350 milliliters.
Show that there wasn't actually any acid in here, except that thankfully wasn't the case, and the paper had instantly turned a reddish pink. This told me that it was quite acidic, and that there was probably a decent amount of acetic acid in there, which meant that I was no longer just going on hope, and I could now move on with the rest of the cleaning.
Okay, so yes, he's got it. He's got his acetic acid. Let's talk more about the quantities that he's seeing, assuming this is about 350 milliliters of acetic acid, or mostly acetic acid. So in this distillation, he got, about 350 milliliters of distillate. That's just an approximation based on what we see in the video. So he started with 1 gallon of glue, and we did a rough calculation that if that glue is pure polyvinyl acetate, it should have 2,950 grams of acetic acid. But we know now that maybe 90% of that material was water. It wasn't PVAc. And so the remaining 10% is actually PVAc. And so 10% of our estimated amount of acetic acid is 295 grams of acetic acid. And based on its density, that's about 280 milliliters of acetic acid. And he just did a distillation and got 350 milliliters. So I think he has really gotten almost every bit of acetic acid out of this, plus some other degradation materials. This is a super promising result.
To do this, I also just kind of made up a procedure that I figured would work, and...
Okay, make up a procedure. These sometimes end badly. Let's see what happens here.
To get started, I dropped in a stir bar. Then into this, I added 400 mils of distilled water, which caused it to immediately turn white, and this was because a bunch of oily stuff that couldn't mix with the water was separating out.
Notice there is some of this biphase, there's some stuff floating on top, there's stuff adhering to the sides. This is probably some of the upper layer of that liquid that wasn't fully separated when he did that liquid extraction. So yeah, that happens sometimes. You don't always get everything separated completely. Now that he's added water, that stuff is even less soluble, and you can actually see it floating on top of whatever's in the beaker.
All of the acetic acid, though, should have easily dissolved into the water, and after letting it sit for a few minutes, I started adding some regular baking soda. This caused it to immediately fizz and bubble as it reacted with the acid in there, which theoretically should have only been acetic acid, and it was turning it into sodium acetate.
This is a nice explanation. This is exactly what's happening. It's reacting with the acetic acid.
As a side product, it was also producing a lot of water and CO2 gas, and my goal here was to basically just keep adding it until it stopped reacting. This is because at that point, all of the acetic acid would be converted to sodium acetate, and I figured that this would go relatively quickly. However, this process turned out to be really slow because every time that I added...
You know, it's weird. Sometimes this kind of stuff, you would think this would be a quick reaction. Sometimes stuff is just slow. It takes time. And it's hard to be patient. Sometimes when things take time, you assume things are going wrong. Sometimes they're just doing what they have to do. But it's hard to be patient and just kind of go through this.
The bubbling took a really long time to settle down, and it was only an hour and nearly 1 kilo of baking soda later.
Ooh, okay. 1 kilo of baking soda. Let's go to a different slide and talk about this 1 kilo of baking soda. Okay, so how much sodium bicarbonate, and that's baking soda, should be added to this? Well, let's assume that he got 295 grams of acetic acid. We don't know what he got, but let's assume that it was 10% of of what we expected from the polyvinyl acetate degradation. That corresponds to 4.9 moles. And since these react in a 1-to-1 ratio, we would in theory need 4.9 moles of baking soda. And 4.9 moles of baking soda is about a little over 410 grams. So we don't need a kilogram. In theory, we need more like a half a kilogram. So with a little bit of math, you could dial in better what your expectations are. I'm not saying it would work perfectly if you added 412 grams, but it's a kilogram is kind of overkill.
When it suddenly stopped reacting. The moment that I saw this, though, I knew that I was finally able to move on from this surprisingly long and tedious step, and what I had to do next was turn on the hot plate. So,
stuff takes a while. That's you know, it stinks, but it happens.
That was what I did, and the goal now was to slowly heat it up and to boil off any volatile organic junk, like the benzene, and then to get rid of any water. The key here, though, was that all of the normally volatile acetic acid was now protected by being in its sodium form, and in theory, once all of this other stuff was gone, I should be left with just solid sodium acetate.
Yeah. Okay. This is a great idea. It's a little crude, but in principle it's great. So this is a salt. Salts are not volatile. Anything else in there that you can heat up and drive away as a vapor, sodium acetate will not be driven off. So you only want the stuff that's left behind after heating, and it should, in theory, be mostly sodium acetate.
So I just kept heating it, and it was really satisfying to see all of the vapors coming off, knowing that a lot of it was benzene and other miscellaneous nasty volatiles. This also went on for a pretty long time, where the temperature just slowly rose, and it was only about an hour and a half later, when all of the volatile crap was gone, and the temperature eventually got to 100 C. At this point, it was probably mostly just water coming...
So whatever's volatile, he's driving off. And this does take time. And the walls of that beaker don't help. They act as a condenser column, in a sense, an air condenser. So sometimes when you do this, you'll maybe try to make sure there's good airflow across the top of that beaker to help sweep away some of those vapors as they're driven off.
Coming off with maybe some residual oil and other trash, and now I just had to wait for all of the water to disappear. The only tricky part was that I had no idea how long this would take, and I was also pretty afraid of accidentally burning all of the sodium acetate, which only got more and more likely as the water content decreased. So, to make sure that didn't happen, I ended up just staring at it, and for another hour, it...
Ended up just staring at it. That sounds miserable, and it is sometimes miserable, but that's a good thing. Sometimes in chemistry, you just got to stare at stuff and watch it.
Really didn't look like very much was happening, until it suddenly started looking like it was getting a bit thicker. Then, over the next 30 seconds, it got thick enough that the stirring had completely stopped working, and not even a minute after that, the entire thing had completely solidified.
Wow, okay, over 30 seconds. Again, quick things happen. You have to monitor what's going on. And so this is presumably salt. And notice that there's still some of this this brown stuff in there. Those are leftover organics. Not all organics are volatile, and so if it's not volatile, it's going to be stuck in your material, and he'll have to deal with that problem.
When I saw this, I immediately turned off the hot plate to prevent it from burning, and I was honestly really impressed with how much sodium acetate there seemed to be.
Listen, I'm impressed too. This stuff has come a long way from a vacuum pyrolysis of school glue. I mean, this is great looking stuff right here.
I mean, there was a pretty decent chance that I'd added way too much sodium bicarbonate, and that was a lot of what was here, but I was still pretty happy with it. At this point though, it was getting pretty late, so I decided to just leave it overnight and to let it cool down. Then, when I came back to it in the morning, I was ready.
It looked better the night before, didn't it? It's as it's kind of crusted up, it's sort of changed appearance.
Ready to continue with the cleanup, and the first thing that I did was add a bunch of acetone. This is because this would easily be able to dissolve most of the impurities that were still there, as well as residual water, except it shouldn't at all be able to dissolve the sodium acetate. So in theory, this should allow me to basically wash the sodium acetate, and over the next few minutes, I just mixed it around as best I could, and I occasionally added some more acetone. During this time, the acetone also slowly got darker and darker, which I was very happy to see, and this told me that it was definitely pulling out a bunch of crap.
So he is pulling out a bunch of crap. I would say those are organic compounds. Organic compounds, just as you use acetone to remove fingernail polish, acetone, well, and that's an organic material, acetone will remove the organics from this. And so he is stripping out, leaching out these organics from this remaining solid, which is presumably sodium acetate, perhaps sodium bicarbonate. But this is looking great. The only thing I would say is that the more you break up those chunks in there, there's some pretty big pieces in here. The more you can break those up, the more you increase the surface area to leach out any of those organic impurities. But clearly he's pulling out a lot because that's some pretty dark acetone.
When I eventually felt that it was done though, it had become a really dark red color, and all I had to do next was dump it into another beaker.
This is the classic decantation. He is decanting the liquid from the solid. Looks good.
I also did my best to not lose any of the sodium acetate, and when I brought it back, I felt that the powder was already looking a lot better. However, it was still quite yellow, which I really didn't like, so I decided to just keep washing it with acetone until I felt that it was super clean.
Successive washes, that's what it takes. So he's doing successive washes of this material with acetone to leach out every bit of those organics as possible.
After a few washings, I also started heating the acetone and bringing it to a boil just to really strip off any crap, and each time I thought that it was really satisfying to dump off all of the dark liquid. I then did what felt like a million more washings, where eventually the hot acetone was only turning yellow and the powder was looking way better, and I felt that this was good enough.
That looks beautiful. He called it good enough. Oh, okay. It's not completely white, and sodium acetate should be a white solid. But life is full of good enough, and to me, that looks awesome.
So I quickly got rid of the acetone, and I did my best to transfer everything to a large dish.
Beautiful.
I then just let it sit there for a day or so, with occasional stirring to get rid of any residual acetone, and when the smell of acetone was eventually completely gone, I put the entire dish in my vacuum oven. I did this just to really make sure that it was absolutely dry, and when I eventually felt that it was looking good, a few days later, I took it out, and what I had now was some nice and crunchy powder. More specifically though,
Dang, if you would have told me you can do it, you would get nice looking white powder. Now, we don't know what that is, but we're assuming it's mostly or exclusively sodium acetate. This looks great. It's come a long way, baby.
This was a bunch of completely dry sodium acetate, where pretty much all of that original nastiness had been removed, and so far, I was very happy with how things were going. This was especially because now I was really close to being done, where the only thing that I still had to do was convert all of this sodium acetate back into some pure and water-free acetic acid. As far as I could tell, this was also relatively easy, and all I had to do was transfer my dry sodium acetate powder.
You fought for all of this distillation, and then to dump it in and spill powder, that stings a little bit. It's a very small percentage of what he has in there, but that lost material, it's so precious at this point. You're almost related to it. You've been with it so long. But anyway, there's a little spillage there.
Powder to a large flask. I then put together almost the same setup that I used for the glue, except this time, above the flask, I included a separatory funnel that I filled with an insane amount of concentrated sulfuric acid. If this ended up tipping over or something, it would have been an absolutely horrible disaster, especially if it splashed on me, and I honestly felt pretty uneasy suspending over 3 pounds of this acid in the air.
Now, sulfuric acid is nasty stuff. It's thick. It looks like water, but it doesn't flow quite as well as water. It's very viscous, and it will absolutely eat you to pieces. If you get a little bit on your skin, you will know it immediately. It will hurt, and you wash your hands. You get it off your skin because it's fast. You can actually feel it getting hot on your skin because it's reacting with your skin and releasing heat. So yeah, you wouldn't want this to spill over.
But with that being said, when I felt that I was ready, I just unleashed the sulfuric acid, and it started bubbling the moment that it touched the sodium acetate. This told me that it was definitely reacting, where in theory, it should have been turning it all back into pure acetic acid and forming sodium sulfate as a side product.
Tell you what, let me get myself out of there. Let's go to the right. Okay, now we can see the chemistry.
It was also generating a lot of heat, which was enough to boil off the acetic acid and to fill the flask with a bunch of white vapor. This white vapor was then traveling out of the flask and...
Now, he mentioned before that he thought he had excess sodium bicarbonate, which is, by the math, I agree, 1 kilogram is too much. If you saw how much it was fizzing, that could be because it was getting hot and boiling something. But it could also be that he was neutralizing that excess sodium bicarbonate, and that was releasing CO2. So I kind of suspect most of those were CO2 bubbles rather than boiling water kind of bubbles.
And down the condenser column and filling the receiving flask. Then after that, it wasn't long before I saw my first drop coming over, and at least theoretically, this should have been some nice and pure acetic acid. Also, because I'd put so much effort into drying the sodium acetate, and because I was using sulfuric acid.
So, and that's maybe an awkward place to pause it. I do want to apologize here. I am, by putting my picture down in the lower left, I am covering the NileRed logo. That is not intentional. It's just I tend to think of reaction videos in the lower left. So anyway, I apologize if anybody's bothered by that, but I'm not trying to show up anybody.
Which really liked to suck up moisture, all of this acetic acid should have been completely water-free. But with that being said, this process was pretty simple, and I basically just had to keep adding the acid. Then, when I was eventually done adding it, all I had to do was swap the funnel for a thermometer and turn on the heating, and go until I stopped collecting any acetic acid. However, I had no idea how long this was going to take, and just like many of the other reactions that I'd done so far, it ended up feeling like it was going on forever.
Distillations always feel like they're going on forever. That's actually a sign that you're doing it right. If it feels like it's going on forever, you're probably doing the right thing, because they typically take a while. So yeah, he just got to drive out all that acetic acid, and he'll do that with heating.
At some point, I also noticed that the stuff I was collecting was slowly getting more and more yellow, meaning that some sort of impurity was somehow...
Yeah, it has just a tinge of being yellow. But notice, that looks way better. That yellow is nothing like the yellow of the degradation of the polymer itself. This, yes, it's not completely colorless, but this looks good. This looks really good.
How making it over, which was kind of concerning. But either way, after a couple hours, I basically stopped collecting anything, so I turned off the heating, and left in the flask was just a nasty mixture of sodium sulfate and carbonized junk, along with some extra sulfuric acid.
When sulfuric acid mixes with stuff and sits and it cooks, it's going to look terrible. I forgot to mention this, but with his vacuum pyrolysis flask, he never showed what was left in the bottom of that flask. And I bet that looked at least as horrific as this flask on the screen. In fact, I would love to know if he actually cleaned that other flask or if he just said, this is not worth the trouble. I'm just going to toss this. Because sometimes glassware just gets so gross, it's not worth the time, the solvents, the effort to try to clean it up.
This was also trash that I didn't need anymore, and the only thing that mattered was what was in the other flask, which, according to my plan, was supposed to be super pure and absolutely water-free acetic acid. Unfortunately, though, nothing ever goes to plan, and the fact that it was yellow told me that it for sure wasn't pure, and that I was going to have to do a bit more work.
Yeah, he's right. It's not pure. It's not 100% pure. But you know what? Nothing is 100% pure. things can get very close to 100%, but there's always going to be impurities. So listen, I think this looks great. He's being setting a really high bar for his standards. This looks really good, super promising.
This wasn't ideal, and it kind of felt that at this point, this cleanup was never ending. But on the bright side, I felt that this would be pretty easy, and that I would just have to quickly distill it again. Except, long story short, it was not easy or quick.
If it's a distillation, it's not quick. It stinks, but it's true.
This was because it turned out that not only was it dirty, it actually wasn't even close to being water-free, and there was apparently an insane amount of water in it, which I think came from adding way too much sodium bicarbonate. So unfortunately, even after distilling it, it was still full of water, and it didn't seem like just doing the same distillation again was gonna work. I really needed it to be perfectly dry though, which meant that I was gonna have to somehow fix this problem, and thankfully, after...
Yeah, this that's maybe an awkward cut there. This is a problem. Getting water from acetic acid is really hard because they are completely miscible, and they have great affinity for one another. So having water in there, and it's almost unavoidable, you're going to get some water in there. Getting that back out is no picnic.
After spending a long time searching online, I ended up finding something on the Science Madness chemistry forum that seemed like it would work. So I decided to just go for it, and the first step was to take all of my acetic acid and to add a bunch of solvent called dichloromethane, or DCM for short.
Okay, this is dichloromethane is a solvent. You know, you talk about different impurities. I'd probably rather have benzene as an impurity than dichloromethane. Dichloromethane is not the nicest stuff either, but it is a solvent, and apparently acetic acid is freely miscible with it. And note that water is not soluble in dichloromethane, but acetic acid is soluble in water and it's soluble in dichloromethane. So acetic acid is allowing these two solvents to mix together. And so this is making a uniform, homogeneous mixture.
Then on top of this, I added some magnesium sulfate drying agent, which would pull out a bunch of residual water, and after letting it stir for a while, I filtered it all direct.
So magnesium sulfate, if it's anhydrous, reacts with water, and it can complex a lot of water molecules. So this is a standard way to get water out of especially organic solutions. And so that's what he's done. He threw some stuff that basically chemically binds the water to get the water away from the organic material.
Into a large flask. By doing this, I was able to quickly get rid of all of the magnesium sulfate, and eventually I was left with a nice and clear solution, which should have already been a lot drier.
This is, so yeah, you chemically bind the water into the solid state, and then you can just filter off that solid material, and you get your product. So he refers to water. I suspect that he's gotten rid of all the water at this point, and we'll talk about that a little bit more in the video here.
With that being said though, I then set it up for yet another distillation, except this time I included this really long piece of glass, which is something called a fractionating column. This is because it would allow me to do a fractional distillation where I would get a much better separation of water and acetic acid, and I just went ahead and cranked up the heating.
Crank up the heat. So methylene chloride boils at close to 40 degrees Celsius, which is way lower than acetic acid. So he added all that dichloromethane, which I protested. Oh, that's terrible. But he can remove that. He can remove it because it's so volatile, and he'll be able to pull that off. And then he'll be left with, hopefully, his dry, clean acetic acid, and he can distill that over a second.
The idea here was to then first distill off all of the DCM, which would come over at around 40 C, but the important part was that it wouldn't distill off alone, and it was supposed to pull any remaining water along with it. This was also exactly what seemed to be happening, because all of the DCM that was coming over was looking cloudy, which told me that it was full of water.
So he's correct. When water mixes with dichloromethane, it is cloudy. To my knowledge, boiling something with dichloromethane will not remove water. It's called an azeotropic distillation. And I don't believe dichloromethane forms an azeotrope. But then the question is, well, then what is this cloudiness? Because that's probably water. I agree, 100%. That is probably water. Sometimes glassware holds a lot of moisture in it. And so my hunch is that that's probably cloudiness from moisture in the glassware rather than the dichloromethane somehow driving out water as it distills.
What was then a very good sign was that as I kept collecting it, the drops slowly cleared up, meaning that there was less and less water, and when all of the DCM was eventually gone, the temperature started rising. I then waited for it to get to exactly 118 C, which was the boiling point of acetic acid, and when it eventually got there, I waited about 30 seconds before quickly swapping the flasks. At this
Okay, so the receiver flask, you're done with one fraction, you swap out the flask, put it in a nice clean one, and here we go, here comes the acetic acid.
everything that I was collecting should have been absolutely pure and completely dry acetic acid, and something that I noticed was that unlike all of the other distillations, there wasn't any fogging or smoke. But either way, I then continued collecting everything that came over, and the moment that the temperature started dropping below 118 C, I ended the distillation. I then took everything that I got.
So he got conservative. So now, before he was going after as much material as possible. He wanted to get everything. And now he's like, hey, I just want to get the best stuff. Because he knows he has plenty of material. So let's just get the best stuff.
And I carefully poured it all into a nice bottle, and what I had...
Okay, boom. So what is that? That, get me out of here, put me to the bottom. Bam, right there. Right there, that's 100 milliliters. This looks like about 100 milliliters. Now these bottles, these graduations aren't super accurate, but they'll give you an idea. So that looks like about 100 milliliters. That's pretty good. Okay, I had to get my lights on so it wasn't so bright on my face. So okay, here we go. He's got about 100 milliliters of this material.
And now should have been 100% pure acetic acid. The only sad part was that the amount that I ended up with was only around 100 mils, which was less than half of what I started with before trying to dry it.
But honestly, this looks pretty good. Theoretically, if the material was 90% of water and only 10% of polyvinyl acetate, I think the most he could have gotten was about close to 300 milliliters of acetic acid. After all this has been through, he's got 100 milliliters. That's a ton. This is massive success. I mean, major kudos for this. This is great stuff.
However, this still should have been more than enough, and I was extremely happy that I was finally done this part, and that I had some theoretically pure acid. To actually know for sure that this was acetic acid, though, I was going to have to do some tests, and
Now, I will say, there's more in this bottle than 100 milliliters, so, this sometimes this comes from B-roll afterwards, and I think this is some B-roll footage.
Decided to start with the easiest one, which was to just see if it smelled like super strong vinegar. Okay, that's definitely acetic acid. So, at least from this quick little acid-smelling experience, whoa, I was almost certain that this was pure acetic acid, but to fully prove it, I was of course going to have to do some real tests. So, the first thing that I did on it was an FTIR, which I then followed up with an HNMR.
He has his own IR and his own NMR. This is high-end stuff. This is pretty cool.
And I was very happy to see that both of these together fully confirmed that this was for sure acetic acid, and that it was quite pure.
I don't put any stock in an IR spectrum, but this NMR, this looks great. Let's not interpret the NMR, but that looks really good. This is very compelling data that he has acetic acid of high purity.
What I was most happy about, though, was that I could finally move on to the next and final step, where I would get to turn all of this acetic acid into pure ethanol, and again, in theory, there were many ways to do this.
He looks pretty excited. He should be. He's come a long way on this.
The only tough part was that, at least initially, every method that I found seemed to have some sort of major downside. After hours of searching, though, I ended up finding this paper, which described a process that appeared relatively easy, and it was supposed to have close to a 100% yield. In my mind, this was also by far the most promising method, and it seemed like it was my only real option.
Okay, now that's his flask. That's about 100 milliliters. So he has all these different methods for doing this reduction of acetic acid to ethanol, and I agree all those look like a pain to produce or to reproduce or perform on his material, but he found something that he thinks is going to work.
And I decided to give it a try. So I just went ahead and jumped right into it, and the first thing that I did was go over to my solvent cabinet, and I pulled out my DMSO. I then started pouring about 200 mils of this solvent into a large flask, and when it was all loaded in, I turned on the stirring. After that, I lowered in a little tube that was attached to my argon tank, and I started shooting in argon to push out all the air. I don't think this was absolutely...
I'm not sure this is necessary, but, it's better safe than sorry, of course.
necessary, but at the same time, this reaction was going to produce a lot of hydrogen gas, and I was kind of paranoid that it could mix with the air in the flask and potentially explode. But with that being said, the flask was now full of argon, and what I had to do next was add the first main ingredient, which was a bunch of white powder. This was all something called sodium borohydride, which is a strong reducing agent, and very soon, this was the stuff that would be releasing the hydrogen. Right now, though, it was still relatively tame, and when it was eventually all added, I let it stir for about 10 minutes.
So sodium borohydride really doesn't do anything with DMSO, which is the solvent that he has in there. So everything's just getting nice and mixed and homogeneous.
Just to give it some time to dissolve. Then, when I eventually felt that it was looking good, I went and got the second main ingredient, which was 9.6 grams of my beautiful acetic acid, and I started to slowly add it.
So this is about 10% of his alcohol. So he's being conservative, but that's about 10% of what he got from his distillation.
This almost immediately caused there to be a bunch of bubbling, along with a pretty clear fizzing sound, and this was because the acetic acid was reacting with the sodium borohydride and releasing some of that hydrogen gas that I mentioned earlier. More importantly, though, it was supposed to be forming an intermediate known as sodium triacetoxy borohydride, which right now might not look like anything useful, but it'll be very important in a bit.
You know, I don't know exactly how this reaction works. This is good enough as anything. This is probably how it works. It's a reducing agent. You typically wouldn't use sodium borohydride to reduce a carboxylic acid, but under these conditions, you're apparently forming reactive intermediates that allow the reaction to occur. So this is fine.
Also, I should mention that the 9.6 grams that I was using here was only around 10% of the acetic acid that I had, and this is because at this point, I still had absolutely no idea if this reaction actually worked, and I was too scared to risk more than this. But anyway, once I'd added everything, I again had to let it stir for several minutes to make sure that it all fully reacted. While this was happening though, I had to prepare the next major ingredient, and to do this, I started by adding an addition funnel above the flask. With this in place, I then went and got another chemical called methane sulfonic acid, and I added 53.8 grams of this syrupy liquid into the funnel.
Yeah, that is not the most pleasant material to work with, methane sulfonic acid, but he's doing it.
On top of this, I also added another 200 mils of DMSO, which
I would not use an addition funnel as a mixing chamber like this. I'd probably get things pre-mixed and then add them together pre-mixed, but it's working for him.
Which easily mixed with it, except in theory, I probably shouldn't have been adding a solvent to an acid. I mean, in this case, I knew it would be fine, but that can't always be assumed. And for example, if I'd done this with sulfuric acid and water, it probably would have boiled and potentially sprayed out of the funnel. But either way, once it was all mixed, I sealed the top with a stopper, and now I was ready to make some ethanol.
Okay, let's go.
So I just went over to the valve on the addition funnel, and I very carefully opened it to dropwise add the methane sulfonic acid, and almost immediately, I could see that it was reacting. This was because there were a bunch of very small bubbles that quickly appeared, which was all hydrogen gas, that was forming as the acid attacked the sodium borohydride. As far as I know, though, this was mostly just a side reaction, and what I actually wanted the acid to do was catalyze a reaction between the sodium borohydride and the sodium triacetoxy borohydride that I made earlier. The paper itself, unfortunately, didn't give any details about this reaction, but what I think is likely is that the sodium borohydride was splitting apart the sodium triacetoxy borohydride and turning it into something called acetaldehyde. This was then probably getting attacked again by the sodium borohydride, which would be reducing it even further, and hopefully turning it into some amazing ethanol.
I don't know the exact mechanism. It's as reasonable as something I propose. We can quibble about stuff, but it worked. The fact is, it works. It's a literature procedure, and he's going to get his ethanol.
Overall, I thought that this was all pretty exciting, except what did concern me was that the paper also didn't give any real details about the reaction process itself, and unfortunately, even though it was still very early on, it was looking like it was going to be a temperamental one. This is because after barely adding any acid, it was already warming up, and at this point, it was getting up to around 40 C.
And that's not terrible. When you mix stuff and it reacts because something from that's unstable is becoming more stable, and that releases heat. And so things warm up. You don't want them to warm up to the point that it's a runaway process, but this is not a surprise. And 40 C is not super hot.
It was also looking like it was slowly getting foamier and foamier, which would only get worse as it heated up, and I was definitely going to have to cool it down. So I just quickly added a large dish under the flask, and I filled it with a bunch of water, and this very quickly brought the temperature down to around 15 degrees Celsius, which I was very happy to see. This is because the crisis seemed to be over, and even though it was still bubbling, it appeared to be much more controlled, and now I figured that I just had to add the rest of the acid. So that was exactly what I did, and what I thought was really interesting was that as I added it, the reaction seemed to go through a few different phases. For example, for some reason, despite the cooling, it all started getting frothier and frothier again.
These hydride reagents, they go through multiple stages. They're kind of flaky reactions, as it's borohydrides and aluminum hydrides, and probably other hydrides for that matter. But they are, they have their own personalities, and you just have to roll with it.
Except right when I started getting concerned that it might eventually foam out of the flask, it all suddenly thinned out. This then made me think that I was basically in the clear and that I was past the worst of it, but then it suddenly started thickening way worse than before, and it actually ended up completely freezing. At the same time, it was also slowly puffing up, which was very concerning, except it again just suddenly started thinning out, and it wasn't long before it completely liquefied.
Yeah, man, it's crazy, and it is weird to watch, but this can happen.
This constant back and forth, though, made it so that I absolutely didn't trust it anymore, and I became constantly worried that at some point it could just start foaming uncontrollably, except that thankfully never happened. This is because it actually ended up being super tame, and when I eventually added the last bit of acid, I was left with a nice and slightly gray solution. At this point, though, the reaction wasn't quite done yet, and I was gonna have to let it stir like this for a bit longer, so while I was waiting, I went and got a beaker.
Okay. I'll note, and maybe I've missed it before, but he has, this is a NileRed beaker. That's pretty deluxe. You got your own glassware, and it looks like it's been well loved. The markings are almost worn off of it. So he's had this for a while. That's a well-used piece of glassware. Not all glassware in lab lives to see that many uses, but apparently this one has. Sometimes they get broken.
Beaker, and I added about 180 mils of water. Then after that, I dumped in 20 grams of sodium hydroxide drain cleaner, and I turned on the stirring, and I waited for it to fully dissolve. When this eventually happened, I had a nice and clear solution, and at this point, it had been about 15 minutes, so I went back to my reaction, which now should have been done, and I started pouring all of this into it. This strongly basic solution was then quenching the reaction, and it was destroying any sodium borohydride, or...
This is maybe something that I would do with an addition funnel, just as you add the acid dropwise, add that base in dropwise, gives you a little more control to add it in small portions. But, it's working for them, it's fine.
Acid that remained. For whatever reason, it also caused the whole thing to clear up quite a bit, and I started noticing little drops of something oily appearing on the side of the flask.
Now, I gotta admit, I personally may not always notice little tiny droplets on the side of the flask. So the fact that he noticed that's great observation, because it's easy to say, it's cloudy, whatever, who cares? And then you got a problem later. But he apparently picked up on this super quickly.
Flask. But moving on, what I had to do next was get all of the ethanol that I hopefully made out of this mixture of chemicals. According to the paper, this was also relatively easy, and apparently, all I had to do was some more distillations. So...
Oh boy, more distillations. It's never fun.
I just immediately got started with that by getting rid of the water dish, and then I quickly added a stopper, a fractional column, and another stopper, and I put together pretty much the same setup that I just did for the acetic acid.
Listen, I love this. He's doing this process. He's not messing around. He's not he's not transferring everything, and you sometimes lose stuff in transfers. He's got a reaction flask, let you stopper that thing up, and run the distillation right out of the reaction flask. So he has potentially water in there. He has some salts. Those aren't going to distill. He has DMSO that has a very high boiling point. And he's got his ethanol. So he's going to go after that ethanol.
Acid. I then cranked up the heating, and it wasn't long before the first stuff started coming over at around 35°C, which I assumed was that oily junk that I saw before. More specifically, though, I was pretty sure that this was all something called dimethyl sulfide, which was supposed to be a...
So let me move myself up a little bit. So dimethyl sulfide, yeah, I mean that is a product that comes can occur in reductions involving DMSO, and so that's not a surprise. Actually, the presence of dimethyl sulfide actually implies maybe the mechanism that was proposed is not exactly the mechanism, because otherwise DMSO is not part of that mechanism. But somehow DMSO is getting reduced to dimethyl sulfide in this process.
Major side product in this reaction. The only unfortunate part was that it was also supposed to smell absolutely horrible, but at such a low boiling point, I figured...
I will say dimethyl sulfide, that comes from many reactions, including something called a Swern reduction. And when you do a Swern reduction, He's right, it stinks. You make dimethyl sulfide and it reeks. But when it's really faint and really light, it smells almost, at least I think, it smells almost exactly like a pumpkin when you open up a pumpkin to carve a pumpkin. And that has a very characteristic odor. And I feel like that the dimethyl sulfide smells exactly the same way. And I'm going to fix my lights here. I just got to roll back. Oh, you're still here. There we go. Okay, let's keep going.
That it would be removed pretty easily. With that being said, I then just kept collecting it until the temperature suddenly started spiking, and when it eventually got to about 80 C, I swapped the flask for a fresh one. This was because at this point, if there were any ethanol in there, this was when it would start coming over. The only tricky part was that it wasn't going to be coming over as pure ethanol, and it would instead be a combination of ethanol and water.
And this is, if you have water mixed with ethanol, water and ethanol do form an azeotrope, and they distill together. So he's right. You're going to get a mixture of ethanol and water. But that's a standard thing. That's fine.
This in turn meant that to get all of the ethanol, I was also going to have to collect all of the water that was in there, which was around 200 mils. And over the next couple hours, the volume in the flask slowly rose. At the same time, the amount in the main flask slowly went down, and with less and less water, a bunch of solid stuff started forming, and this was all just junk from the reaction that was being left behind.
So he has salts, and he has residual DMS, certainly some DMSO left in there as well. So that's probably the liquid, and then who knows what boron salts are still in there. Those are some of those solids.
Going back to the other flask, though, it did eventually get to the point that it was around 200 milliliters, and right when this happened, I turned off the heating. I then quickly popped off the flask, and what I had now was, at least in theory, around...
It looks like he still has some of those droplets in there, right? Some of those dimethyl, what he thinks might be dimethyl sulfide droplets. So that's not encouraging.
5% ethanol, which I thought was pretty exciting. However, just by looking at it and seeing all of the little oil drops that were still somehow floating around, it was obvious that I was going to have to clean it a bit more. So I decided to do another distillation, except this time I would use a much more efficient fractional column.
So when you do this, there are different distillation columns. He's doing a different one that should, in theory, be more effective at removing the dimethyl sulfide. Maybe not perfect, but successfully keep trying to reduce it to a lower and lower level,
which would hopefully give me a better separation of ethanol and water. I then just went ahead and cranked up the heating, and I basically did the same thing as before, where I rejected everything that came over below 80 C. The major difference this time, though, was that I wasn't going to be collecting all the water, and I was actually going to try to leave behind as much as possible by pulling off the flask the moment that the temperature got to 100 C.
So notice how this always is. Initially, when you do something, it's like, I want everything. And then once you get everything, you realize, oh, I really didn't want everything. Now I'm going to be pickier, and I'm going to be selective in what I take off. But the fact that he got a lot of material tends to give people the confidence to say, okay, I'm going to be a little pickier this time around.
So that was exactly what I did. And then I very carefully transferred everything that I got to a little vial. And at this point, I was pretty happy with how things were going. This was because, assuming that the reaction had worked, what I had now should have been relatively clean ethanol.
So, and this is pretty nice. This is, remember, he started with like 9.6 milliliters of acetic acid. And here he is at, that's not 9 milliliters, but he's going to lose something, and ethanol has a lower molecular weight than acetic acid. So in the transformation, you're going to lose some mass regardless, even at 100% yield.
To fully confirm this, though, I was going to have to run it through my NMR, so that was what I did. And well, it told me that it wasn't super pure, but it was for sure ethanol.
Okay, this is worth stopping on. Note this peak right here. This is actually, and this is going to be important later, this is about where dimethyl sulfide should appear. Now, I'm not saying that this is dimethyl sulfide, but this is consistent. So, this is evidence. This could be dimethyl sulfide. Otherwise, this looks pretty good. There's a little extra junk down here, but that's okay. This looks good. I mean, look, it looks really good. Okay, I'm being picky, but it looks great. This is ethanol.
To get its concentration, I then did another test by putting a few drops of the ethanol onto something known as a refractometer, and when I looked into it, it told me that it was at least 80%, which was actually better than I expected.
That is way better than I would have expected. That is really, really good. Okay.
The only unfortunate part was that when I went to do the very necessary smell test, I was not very impressed. This is because instead of getting a nice and clean ethanol smell, it was almost unbearably sulfury, with a horrible rotten cabbage stench.
Yeah, that peak of the NMR, that showed it. That's consistent with it. And then the nose test says, oh yeah, you have some sulfur compounds in here.
Also almost immediately knew that this was all coming from residual dimethyl sulfide, which was somehow able to make it through the distillations, and I was honestly getting a bit worried that this might end up being a problem. At the same time though, I felt that it was probably fine, and that it could be easily removed with some more distilling, and instead, I decided to focus on how well this reaction had worked. I mean, the yield wasn't even close to the 93% in the paper, and it was more like...
Okay, so he's looking at this reaction. Let's move me to the bottom. These are reduction yields by NMR spectroscopy. So they haven't isolated the product. They've just taken an NMR spectra to determine the percent conversion. And measuring conversion is totally different from actually isolating pure product. So yeah, this 93% is almost meaningless based on what yield you're going to get. So no, I agree. This is a really good result.
48% because they didn't fully isolate it like I did, but overall I still really liked the process, and I liked that it was relatively simple and easy. So I decided to just keep going with it and to use it to convert the rest of the acetic acid that still remained.
So at this point, I'm going to zoom ahead on the video a little bit. So he is now going to take the remainder of his acetic acid and he's going to put it through this reduction process and get it all. And then he's going to work with it all together instead of trying to make that first portion perfect. Okay, so we're starting back up. He's now distilled a larger batch, and he's taken the bulk of the material through this process.
8% ethanol. I then took everything that I got and I carefully poured it all into a fresh bottle, and in total, it ended up being just over 80 milliliters. I then brought back the roughly 6 mils that I got from the first run, which together with this was now nearly 90 mils, and this was way more than I ever expected to get.
So by my eye, he had about 100 milliliters of distilled acetic acid. And from that 100 milliliters, he got 90 milliliters of ethanol. That's a fantastic conversion. I mean, now granted, this is not pure ethanol. This has some water in it. And apparently has a little bit of dimethyl sulfide too, but that's a lot of material. I mean, this is, 2 thumbs up. This is really, really good.
Yeah, and I was feeling pretty happy about it. The only problem was that right now, it was all still nowhere near drinkable because it all smelled terrible, and it likely tasted like horribly rotten cabbage. As I mentioned earlier though, I felt that this would be relatively easy to get rid of, and that I would just have to combine everything and do one final distillation. However, just like everything else in this...
So he's distilling this with some copper. Copper can interact with sulfur compounds, but normally those are thiols. They have an SH. Dimethyl sulfide doesn't have an SH. So the copper is probably not going to help very much. Not as if it would if it were a thiol.
Project, that absolutely wasn't the case. And even though I included a bunch of copper, which was supposed to help remove sulfur compounds, the final result that I got was still far from good. That smells pretty bad. I mean, it was definitely better, but it was still nowhere near drinkable, and to get rid of this stubborn crap, it was looking like I was just gonna have to keep distilling it over and over. So...
yeah, it's painful. It's painful to watch. I can't imagine doing it in person.
Oh, that was exactly what I did. And what I did as well was filter it each time through a mixture of activated charcoal and ion exchange resin, which was basically just a deconstructed Brita water filter, and I think it helped. Overall though, not only did this whole process turn out to be really time-consuming and tedious, it was also not very efficient. This was because to make any significant improvement, I found that I had to sacrifice quite a bit of the initial stuff that came over at ADC. This in turn meant that I lost more and more with every distillation, where by the fourth one, I barely had any left.
By the fourth one. So now, again, once you have material, now he's getting picky. And the cost of being picky, though, is you get selective and you lose some material. But of course, you're losing the impurities, presumably, as you do that.
However, on the bright side, everything that I was collecting now was coming over in the very narrow range of 80 to 81C, which told me that it was quite pure. There was also a very good chance that I'd finally gotten rid of that horrible smell, and that all of this stuff here was actually drinkable, which I thought was pretty exciting. It was then only 5 minutes later, when I was getting really close to being done, except what I had collected at this point was honestly a really sad amount of liquid. I mean, compared to what I'd started with, this was basically nothing, and in hindsight, I really should have avoided any method involving sulfur. On the bright side though, at least from what I could tell, it was looking like I'd somewhat managed to salvage things, and at this point, it was done, so I swapped out the vial.
There are other methods that could have been used, and I'm not talking just about, well, maybe I am talking about the reduction, but the other methods would have their own pleasantries as well. So this is maybe, he's got it. I wouldn't look back and second guess. This is working.
Now, all that there was left to do was to see how it smelled, and I was honestly kind of nervous and worried that it would be terrible, and that I would have to keep distilling it until I basically had nothing. That's perfect.
Perfect, okay.
Except that thankfully wasn't the case. I mean, there was still a very slight hint of something else, but other than that, it basically smelled like pure ethanol, and when I ran the NMR, it...
Boom, yeah, okay, let's let him talk here.
It was clearly way better. More specifically, that massive impurity that was here was now...
Yes, remember that peak at, or close to 2? That was likely dimethyl sulfide. That is basically gone. And there's a little extra here and there, but this is great. I love this this benchtop NMR. This is fantastic.
Now just an extremely small bump, and when I compared it to an NMR of some ethanol that I bought at the store, it basically looked the same. I then tested the concentration using the refractometer, which told me that it was about 68%, and it was surprising to see that it was somehow lower than before.
Well, 68% is still pretty darn good, and that's pretty strong alcohol too. That's way stronger than what you'd get in vodka or something like that. So that's it's not 95%, but that's pretty good.
With all that being said, though, I was now finally done, and after what was probably way too much effort, it was looking like I had successfully turned a gallon of children's glue into some drinkable alcohol. I finally did it. What a sad amount. At this point, there was also, of course, only one thing left to do, which was to taste it, and to see if all of this effort was worth it. So, that was what I had to do next, except as a quick warning, I should be clear that tasting anything that I make is always at my own risk, and even if it seems fine based on the NMR and other tests, there could always be something toxic or horrible still in there.
Hey, I think he probably has to put a disclaimer in there. But listen, nobody thinks it's okay to drink chemicals. I mean, we eat and drink chemicals all the time, but this is not food grade material. No one would think this is okay. Everybody understands it has at his own risk. There are some people who really object to this kind of content because it's promoting unsafe activity. I don't think that's the case at all. No more than someone riding a bike and doing stunts on a bike is promoting reckless activity. They're just, they're showing off their skills. So I understand what he's doing, but it's unfortunate that it has to be done this way because people should get it.
But with that warning aside, it was finally time to see how it was, and I was honestly feeling a bit nervous. I guess I just have to go ahead and try it, and I hope I'm not poisoning.
Okay, down the hatch. Drink it.
Okay, I'll just taste it. That's not good. I mean, there's the obvious fact that it's almost 70% ethanol, so it just burns, but it definitely has a characteristic flavor.
It's going to have impurities. It's going to have its own bouquet.
And when I think a bit more about it, it may be definitely some sort of volatile hydrocarbon, like gasoline or something. Definitely has it has a chemical flavor to it. I don't know how else to describe it. Overall, though, is it horrible? No, I think it's totally drinkable if you have nothing else.
Is it horrible? Would you drink it some more? Heck no. You go to the grocery store or the ABC store or wherever, and you get some regular alcohol. But still, that's cool. It worked. It worked from glue, of all things. It's crazy.
I mean, assuming it doesn't have some poison in it that kills you. But besides that risk, it's kind of fine. So, in the end,
kind of fun.
It
Okay.
unfortunately wasn't the amazing alcohol that I was hoping for, but at the same time...
Okay, tell you what, I'm going to wrap it up there. He's just going to archive this material for posterity's sake. Listen, I really enjoyed this video. I hope you enjoyed. Maybe you got some different insight in for you for watching this reaction video and some of my thoughts about it. But it's really a nice video, and yeah. I hope you enjoyed it, and thank you again for watching, and take care.